Okay, so in this video, we're going to look at what we call pulse width modulated DC-AC converters. So we've already introduced the concept of the DC-AC converter, and we've seen that it is essentially a DC-DC converter, but what changes is the way we switch, or the control of the switching states, essentially, right? And when we discussed DC-DC converters, we said that the output voltage of, for example, a buck converter would vary between 0 and VI depending on the duty cycle. So we said that it was true for basically all of the all of the DC-DC converters. We said that the output voltage depends directly on the duty cycle. But in those cases, we saw that the duty cycle was a constant. It was a fixed value. Now, let's try to imagine for a second, and this is going to lead into the discussion of pulse width modulated converters, but let's imagine for a second that we have a buck converter, okay? So we're going to have a buck converter that looks as the buck converter looks. So there'll be an input capacitance, your switch here, diode, and then we're going to put an output filter here, L, and then we'll put a C, okay? This second capacitor here is, it's part of an output filter, second order LC filter. We've seen it with the single filter, which is just the inductor. It makes no difference to the overall functionality of the circuit. But in the case of talking about inverters and all that kind of stuff, it might be a bit more realistic to have something like this. So if this is VI, or I guess we've called this V1 in the past, so let's call it V1. And let's say this is V2, and we have here our C, L, D. We can call it C1 maybe. We're not going to do any calculations with these, so this is really just for the purpose of being able to refer to them properly. So, remember, we said, what did we say? We said that that the output goes between 0 and VI depending on D, right? So we said that V2 essentially equals D times V1, right, or VI. Now, what happens if D, or the duty cycle, is a variable, right? So let's say V2 equals D as a function of T times V1. So it's a time variant function now. So if D varies, the duty cycle varies with time, but a very critical aspect here is that it varies with respect to time, but very slow relative to the switching frequency. So what that means is if you have a 1 kilohertz switching frequency, then D of T can vary, let's say, with 50 or 60 hertz. Or if you have a 10 kilohertz, then you can vary comfortably with 60 hertz. So if D of T varies with 60 hertz frequency, and the switching frequency is 10 kilohertz, this is valid. But you can't have D of T varying at a frequency that is close to the switching frequency. Otherwise, this entire analysis does not hold, because it assumes essentially that we're talking about averages here, right? And so averages are only true at certain time scales relative to other time scales. So again, it's only true if you have D of T varying at a slow rate relative to the switching frequency. So if we have this, now suppose for a second, if we say that D of T equals 0.5 plus 0.25 sine, let's call it omega AT, okay? Now if this is the case, and again, as I've done in the past, I'm going to cheat, okay? And so if I'm going to cheat, I'm going to pull in this waveform here. And essentially what we see is this 0.5 plus 0.25 sine is this V2 here. And what we see is that this switching frequency is much lower than this frequency, obviously. So another thing we see is that the pulse width varies over the time, because what it's doing is it's taking on that value for that switching cycle. So whatever the value is here, it's taking on that value of the pulse width, right? So D of T, for instance, at that point in time, you can evaluate it and it'll be something. So if this equals pi, if T equals pi over omega A cancel, right? You end up with a maximum here. And that's 0.75 because that's 0.5 plus 0.25. And so if you have that here, then you see that this is the largest pulse width that you can have. And so this continues, right? And so again, we see that now you can create V2. And again, this is only after all these harmonics are filtered, right? So the convenient part of doing it this way is that you can filter all of these higher order harmonics and you'll be left with the average voltage. And the filtering is obviously done by this combination of the LC here, but the average voltage will be a clean sinusoid, relatively clean sinusoid. Right, so I guess we should also label this, because VD is really this voltage here, right? So VD is a switching waveform. So it's a PWM waveform, we say, with a DC component and a fundamental component. There are also additional harmonics, but they're above the switching frequency, and we can filter them out using an LC. And obviously the higher the switching frequency, the higher these harmonics will be, and the easier they are to filter with this LC pair. So the advantage of high frequency PWM is that the unwanted harmonics all end up being at higher frequencies, so they're easier to filter, right? So we see that based on, again, DC-DC converters and relatively straightforward stuff that we've seen in the past, through, again, fairly straightforward circuits like the buck converter is a very common circuit, just by varying the duty cycle. And the duty cycle is obviously, let's say, this thing here that's driving the switch. So we see that we can create here a sinusoid. And of course, this applies to all types of other circuits as well. But what we're going to do is we're going to now look at how can you actually generate D of T for a PWM inverter, because it's important to understand how a waveform like this can be generated, right? Because we see here just a bunch of square waves, or well, what looks like a modulated square wave, we should say. But how do we actually generate this type of waveform? So the way we do that is first of all, I should say there are many ways to generate PWM. And PWM itself, there is a whole area of research dedicated to modulation techniques and which one is best for which type of applications and so on. And there are a number of them with multiple carriers and sort of software techniques and all this kind of stuff. But in the simplest case, at the end of the day, what PWM comes down to, if you want to look at the generation of this D of T that we said, this duty cycle, if we want to generate this duty cycle from a couple of waveforms, how do we do it? So the simplest way is this. You have a comparator, right? So I mean, this is I guess, circuit implementation, but you can obviously do this type of stuff in software these days, which is usually where most of these things actually happen. Some type of microprocessor, microcontroller, FPGA, DSP platform, something like that. So if this, let's say, is VS, and let's say this is VT, and VS stands for V signal, VT stands for V, I guess, triangle, because usually what you do is you compare your reference signal, or your modulating waveform as it's called more often, with a triangle. And the triangle being literally just a triangle wave that it goes up and down, or some people even call it a counter, right? So it goes up and it goes down, it goes up and down, constant frequency. So that's your switching frequency, right? Kind of like we did with DC-DC converters, but the same thing. But what's happening here is the comparison that's happening is happening with a time varying signal. So VS is time varying, and I guess we can call this G of T like this. And so we see that it's a time varying waveform. And if it's a time varying waveform, the duty cycle that is, then what we end up with is a time varying average. And so what does this time varying average look like, or this whole situation look like? Again, we're going to cheat because these waveforms are very difficult to draw accurately freehand. And so what we see here is that VS is some sort of, let's say, again, this is a different example now, we're not looking at the sinusoid anymore, but we're seeing that it's some type of rectified waveform, right? And so if we see that this is rectified here, so we see that this is D of T basically, or it's going to govern, it's going to dictate what D of T is. So we see that at this point, you see that there's no, this is off at the bottom, right? So wherever these intersections happen, that's where the pulses go high. So what we say is that, again, this is a comparator, right? So whenever the signal, VS, is higher than VT, G will be positive, right? And whenever VS becomes lower than that, G will be 0 in this case. So we see that there are these intersections here, right? So we see there's an intersection here, there's one here, here, and so these are the sort of switching instances that we expect. And whenever the VS waveform is larger than the triangle, then we see that the pulse goes high, right? So we see that between this time, obviously it goes high, then we see that it's off between this, then we see that it's high again between these two times, and so on, and so it continues. And we see that it's a maximum when VS reaches its maximum. So what that means is VS can be any signal, and you can compare it to this triangle, and you can switch it according to this sort of sequence, and you can generate an average that would look like this. Well, sorry, the average would look like VS based on this switching waveform. So again, this is G of T. Basically, it's a gate pulse, right? So your switches should be turned on and off according to this sort of sequence, I guess you can call it. So we see that this is a rectified waveform essentially, VS. This looks like a rectified waveform, right? So it has an amplitude of K, and it's being compared to a carrier, which we're calling V of T here, T being triangle. G of T is high whenever the value of the sine exceeds the carrier, obviously, as we've seen here, and the duration of each pulse is essentially a metric, I guess you can say, or a measure of the time that the switch should be on for that thing, right? So we see that the switch should be on for this much time here, depending on how these two are related and how high this is. So you're basically creating an average based on the switching sort of sequence that you have. So these pulses drive the transistors of the bridge, and we can control the amplitude of the fundamental by varying K. So what that means is, if I want a certain value, let's say, obviously this is normalized. K has to be normalized to 1, right? So K has to be less than 1. But if I wanted K to be equal to 0.75, let's say, that means what it's going to do is if I go to this case here, it'll give me 0.75 at the maximum case. And so that means this will be when D of T is as high as it can possibly be, then V2 will be 0.75 times V1, right? So that'll be 75%. But now if I want to go to the full scale, then I will let my reference waveform, or my modulating waveform as we call it sometimes, this waveform should be able to go from 0 to 1. So K basically governs the sort of scale over which your output waveform can be, or I guess the actual value itself. I mean, but K is usually fixed with an upper limit, right? So you can have some upper limit, and obviously the hard upper limit is 1, right? Because you can't exceed that. Well, you can, but overmodulation is a different thing, and we'll probably get into that at some point later on. But K is referred to as the modulation index, and using the modulation index, we can control the average value of the output waveform. So that's one way to generate PWM. There are other ways to do it. So in a full bridge, for instance, because this is a sort of a general concept, but in a full bridge, sometimes it's useful to have the same carrier for all of the switches, and to modulate the switches so that they all see the same frequency as well as the losses. And so there's another way we can generate PWM. And again, this is a circuit implementation, although, I mean, you could probably implement the exact same thing in a simulation software such as Simulink, or even Multisim, I imagine, using their blocks for comparators as opposed to op-amps, because as we know, op-amps are used as comparators quite frequently. So what we're going to see is another sort of modulation technique. So what we have here is we have a signal that comes in like this. This is inverted, and so we're going to have here Vref, and Vref is essentially the same thing as Vs. Sometimes you'll see it called ref, sometimes you'll see it called S. So this is Q1, let's say, and this is Q2 inverse, and this would be Q3 and a Q4 inverse, and obviously we're referring to a full bridge. So the full bridge, remember, looks something like this, and I won't draw any sort of load here because the load is irrelevant in this case. But if this is S1, S2, S3, S4, then what you have is, and obviously this is VDC, then what you end up with is a sequence of gating pulses as shown here. So Q1 and Q2 would be, well, sorry, I forgot to draw one more thing here, and this is your triangle carrier, right? And obviously this is the frequency of this we can call, I guess, this would be the frequency or the period, however you want to call it. This can be, we can call F or FS, however you want to refer to that. But essentially you would have, so the actual reference would drive Q1 and Q2 inverse, and then the negative of the reference being less than the carrier would drive Q3 and Q4 inverse. And since so that's kind of might seem a little abstract, why don't we take a look at another waveform that we're going to cheat with, because again, there's no way I could draw these very clearly by hand if required to on the spot. So what do we see here? We see the same carrier for both, right? And we see that this is a reference signal going up, and this is the same reference signal going down because it's negative. And in this case, VL and VR are the voltages of the left and the right side. And so what we're going to do is we're going to let's try to look at some of these, and we can maybe make sense of a couple of these switching instances. So we see here that, so we say that for Q1 and Q2, that's this top one, right? So this is Q1 and Q2 inverse gets that. Well, I guess it's Q1. Q2 inverse should be the inverse of that, right? So we can call that Q1, I guess is more accurate. Let's call it Q1. And then this one here is for Q3. And again, these two are for Q1 and Q3. But essentially what we're doing is we're looking at, we say that when the reference is greater than the triangle, then switch on Q1. And Q1 is going to be this left side. Okay, so VL and VR correspond to these midpoint voltages of these sort of two legs of the converter relative to the midpoint, virtual midpoint, or sometimes they consider it neutral here. But whatever you're doing, there's either a virtual midpoint, or we can call this point at the bottom ground, and then we can look at it that way. In any case, you see that there are two voltages, VL and VR. Okay, so the left hand and the right hand. And then the difference of the two obviously is going to be the actual voltage that is across the AC terminals. And so we see that if let's take some point where it's actually pretty easy to see. So if I take this and I take this, right? So, well, maybe not those two because that's not what I wanted to do. Let's take this point and this point, right? So what I see here is that this, if I were to sort of extend this down, goes down like that. So we see that those are high, and we see that the reference is greater than the triangle there. We can take another point, let's say here and here, and if we were to drop those down like that, we see that there is a high pulse there. So again, we give the pulse high whenever the reference is greater than the triangle. Okay. Now on the other side, we see that it's whenever the negative of the reference is less than the triangle. Okay, so the negative of the reference is already drawn, which is convenient for us. Now we have to see where is it less than, right? So during this time it's less than here, right? So that means we expect to see that there. So it's whenever the triangle is less than negative of this, right? So again, this dot here and this dot here, if we drop them down, we see that this is here, right? And we can do the same thing here. Well, anywhere really, but I mean, you get the idea. So we have a bunch of these pulses, and these pulses happen relative to these triangle carriers. And then at the end of the day, when you take the difference of these two voltages, because again, that's what you have for this VA here. We haven't labeled VA. That's what you have for this VA voltage here, is the reference, or sorry, is the difference of these two. You see that you'll end up with some waveform that looks like this. And again, this will be a sinusoidal average, supposing these are sinusoidal references. But essentially, this is what we do here. And so we see that this is also a 3-level waveform as well, right? So we're fully utilizing the capabilities of the full bridge. Whereas in a case like this, you might not necessarily be able to do that because of the way that the switching sequence might turn out. But in a case like this, we can. And this is usually referred to as naturally sampled PWM. So you compare the reference to the triangle, and you do that. And there are also, again, there's a bunch of different ways that this can be implemented. So you see that this triangle is, it's what we call a balanced triangle. It's not skewed. It goes up and it goes down sort of symmetrically. But you might have what we call sawtooth waveforms. So it might do something like this, because these are easier to program, right? So it goes up and then it comes straight back down. So these require less memory when they program them, right? Because you can just repeat the cycle every whatever your frequency is. So you don't have to come back down. But that in itself results in different harmonic sort of behavior. But this type of method is usually preferred because it provides double-edged modulation, is what we call it, with PWM pulses that are symmetric around the peaks of the carrier. And symmetric, I mean like the harmonic spectrum when I say that. So the harmonic spectrum will obviously have it's going to be, well, you have the multiplication of two signals. And if you consider the multiplication of two signals, if you remember from the Fourier spectrum, whenever you multiply a signal by a frequency, you basically shift it up and down in the frequency spectrum. And then all of its harmonics will also get shifted up and down in the frequency spectrum, which will then produce a sort of shift in the frequency. And so if you have this type of PWM, you ensure that the harmonics stay, or that the PWM pulses at least, are symmetric around the peaks of the carrier. And you also see that in this case, physically speaking, they are also symmetric about the peaks of the carrier as well. So what do I mean by that? I mean, you have this is symmetric here. So you see that the pulse is equal on both sides of these peaks and sort of troughs. And in the other case, they're not. They're slightly shifted. But you wouldn't know that because we haven't seen that. Well, is it obvious here? I don't think it's very obvious here. It kind of looks the same. So in other cases, you might not get that. For example, in the sawtooth thing that I was discussing. So we've seen here sort of a way to generate this. And again, there are more elaborate ways of doing it. There are more complicated ways of doing it. But essentially, this whole process that we see is repeatable for any converter. This is not unique to a power converter. You can apply this to any topology as long as you know which switch should receive which pulse and what the output waveforms look like. So this is a sort of universal technique, and this is not limited to the buck converter or to the full bridge. So please don't assume that they are. We'll see that you can actually apply this to multiple different types of topologies, as well as you can even have it to like a 3-phase version. You can have, like, I mean, if you want to go higher to like a 6-phase version, you can go to that as well. So there's no limitation really. But the main benefits of this are that you can generate signals that are at very high well, their harmonics are at very high frequencies, and so they're very easy to filter, right? Which is obviously a good thing. And the higher the harmonics, the easier they are to filter, the cleaner your signal can be. But then the trade-off becomes your switching at a higher frequency is difficult, right? So it's not straightforward to switch converters at higher and higher frequencies, especially as switching losses and all that type of stuff become more and more amplified. But as far as this is concerned, we see that this is a relatively straightforward thing. The main benefit of this is that you essentially have a you sample the reference at twice the carrier frequency. What I mean by that is that because you have because of the way that these switching pulses end up lining up, you end up with a higher frequency sort of sampling. I mean, and I put sampling in quotes. I guess if you could see me, I call it sampling because we're not technically sampling, but I mean, I guess the PWM is kind of sampling. But so in that case, it's easier to filter everything when it's at a higher frequency. So this was a sort of a very, I guess, high-level look at PWM. What we'll do in other videos is we'll look at examples as to how you can actually implement this in Simulink with a converter, with different types of things, and actually generate the types of waveforms that you want. We'll look at how you can predict what type of waveforms you get at your output, what the magnitudes of all the different harmonics will be, how you can get the harmonic spectrum in all these kind of things, and figure out what the overall system is behavior is, right? And so for now, we're going to leave it at this. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.